Today we are going to introduce Taylor series. We suppose you have already know the form of power series in the last chapter. And Taylor series is very useful because we can observe some properties of a function or a series by transforming it into Taylor series. Okay. To explain Taylor series, we can first start at an easy function, f of x. And f of x is in the form of power series, and we differentiate f of x and get the first order, second order, and the third order derivative of the function. And now we care about the coefficient before every c of n. Okay, and by observing the first section of each derivative, like this, we know that the coefficient before the first one, the Cn, is n factorial. So we can have the conclusion like this, that the coefficient before Cn is the nth order of f of x and divide n factorial. And please remember this because we will use it to find every Taylor series, so it's very important. There's a special case in Taylor series that f of x, we say the function centered at a. And when a equals 0, in other words, that the function is centered at 0, we call it Maclaurin series. And Maclaurin series is sometimes useful because we can find some function in Maclaurin series to simplify the complicated functions, and later we transform it back to the original function. You may ask, how do we know that Taylor series equal to the original f of x? Okay, to check the equality, we say f of x equals to the Taylor series we find plus r of x, and we call it remainder. If we can prove that the limit to infinite r of x, the remainder equals to 0, then we can say that the Taylor series equals to the original function. Below, I'm going to show that the Taylor series of cosine x equals to cosine x. Okay, like I said, the most important is to find the number n, and we know cosine x is less than 1 for all x. It's trivial, so we choose m. We say m equals to 1. Okay, then we put 1 into the formula, and the remainder look like this. And by calculating its limit, we know that limit in this form is 0, so we say the remainder is 0. By proving remainder is 0, we say the Taylor series of the function equals to the original function. Recall that I've shown how to find the coefficient before every Cn in the first part, and now we are going to use it. I'm going to do 3 easy functions transformation to Taylor series below, and the first one is exponential function, and the second one is sine x, and the third one is arctangent x. And please remember the process because we use the 3 functions very often. Okay. The first one, the exponential function, is the easiest one. By using the method, we find the every order of the derivative, and we observe the coefficient. And the first order, second order, and the third order derivative, we can find that the coefficient is always 1. So we can make an easy conclusion that the coefficient is 1. Okay, then we put it back to the form. We can say the Taylor series of exponential functions look like this. And don't forget, there is an n factorial. The second function is sine x. And I've already write the derivative at the left side, so it's easier to observe. Okay, then now let's look at the coefficient, the value. We can make a conclusion that the coefficient of every even power is 0, and there's only value that's not 0 as the odd power. So we only care about the odd power here, and the value will change between 1 and -1. So it's the first conclusion. There's only odd function left only, so we can demonstrate it in the form. Okay, so we can say the Taylor series of sine x is like this. And there is some important part. The first one is -1 will change by giving a power n. It will change between 1 and -1. And the second part is the factorial and x. Okay, and this is how we find the Taylor series of sine x. The last function is arctangent x, and this is more complicated, so we will not do in the common form. Okay, first it's trivial. We already know that arctangent equals to the integral of 1 over 1 plus x squared. And in this chapter, power series, you can find the power series of 1 over 1 plus x squared easily. And it will look like this. It's the form of 1 over 1 plus x squared in power series. And after we know the power series of the function, we'll do the integral right now. And the integral of the original functions is like this. If you can't find the answer very fast, you can write down the process, and you will not make a mistake. Surely. The first one is 1 minus x squared. We only care about step rows because we can find the rows by this. And the integral will become like x minus x power 3 and divide 3 plus. Okay, then this part is the same as this part. After doing more times, you can observe it very fast. And if you can't, just write down. Then you will not make mistake. Okay, then we say the final part is the Taylor series of arctangent x by doing the integral.
Okay, after finishing learning Taylor series, we now can look at some questions. The questions won't be too hard since we are familiar with the trigonometric Taylor series, so we can easily solve it. So let's look at the first question. We want to find the Taylor series of this function. Okay, now, so as we learned before, we know the cosine Taylor series is this. So by substituting the cosine function into Taylor series, we get this integral. And the next step, we will simplify the function. We put the denominator x into the series. So we'll notice that the numerator on the top is x power of 2n, and now it become x power of 2n minus 1 since we put the denominator into the numerator. And also notice that the minus 1 at the back becomes x negative power of negative 1. And then we do the integration. So we'll get the denominator become 2n factorial times 2n, and the numerator become x power of 2n. This is quite easy since we integrate many functions, and this is just a simple polynomial. And also at the back, x power of negative 1 will become ln x since we integrate it. And this is also easy because it's just the definition of ln. So we get the Taylor series for this function is this. It's quite easy. We just first substitute the cosine function into Taylor series and then do the integration. It's nothing too hard. So let's look at the other question. This one is more easier because we don't have to do integration. We only have to substitute the function. So let's start it. For sine x, we know the Taylor series for sine function is this. So we substitute it and we get y equals to this. And then we divided the numerator and denominator both by x. We will get the numerator become 1. And the denominator, the power of x at here is 2n plus 1. And it will become 2n in here since we divided by x. And the denominator will be the same. It's all 2n plus 1's factorial. And then we will simplify this function by putting 2n plus 1's factorial up to the numerator. And we will get this function. And then we will put the denominator onto the numerator and add negative sign to the power. So we will get that this function equals to this function's Taylor series equals to this. It's just basically we substitute the function and then we keep simplify it. It's nothing difficult in here. So from the questions, we know that it's important to be familiar with the trigonometric functions Taylor series, and we can get the Taylor series for trigonometric functions whenever it changes, like it times by x or divided by x or something like that. Now we will look at the application of Taylor series. As we learned before, we know that by Taylor theorem, we can change almost any complex functions into Taylor series, which is an infinite series. And since with infinite series, we can get the value of the functions by plugging in the variable, which is x from the above example. And by trying some values, we know that the value is quite precise. Here we will look at an example for like we will take sine pi over 10 as the example. Before we learn Taylor series, if we want to get the value of sine pi over x, we may use the half angle formula or the double angle formula or even the triple angle formula to get the value of sine pi over x. But now, since we have Taylor series, we can just simply plug in the number. So as we learned before, the Taylor series for sine x is this. And Taylor series is an infinite series, but we can't calculate infinite items. So in here, we will only take the first 3 items. You may think that the first 3 items are it will maybe get a very rough value, but we will prove that it would not. It will get a quite precise value. So the first 3 items for the Taylor series is this. And we plug in pi over 10 for x. And we will get, we use the calculator to calculate the value, and it will be 0.30902. And by just simply use calculator to calculate sine pi over x, we get 0.30901 and more. So we can see that we only use the first 3 items, but the value is already quite precise. And with the application of computer, we can define the trigonometric functions as Taylor series, and then we let the computer to calculate the value. Since the computer is good at calculation, it can calculate many items, and it will almost be the value it calculates will be almost the real value of the complex functions. This means that we can get almost any value for complex functions with computers, and this is a very good news for maybe physics, chemistry, or engineering, since we can get the value for any functions by using Taylor series. Okay, so this is almost all the things that we will cover in this video. Hope you learned something from this video.